Now let's talk about how to simulate non-planar reflections. And this brings us to the so-called cube maps, a very popular approach to simulate reflections at arbitrary surfaces. And what the basic idea behind a cube map is, or the cube map is just a texture map, or more precisely, a cube map is, let's say, a texture which is comprised of 6 textures. And what we do in order to compute these textures, we compute images of the surrounding environment when looking from the center of a cube through all the 6 cube faces. That is what we see here in this image. So imagine that we specify a point, the center point of that cube, or let's say we first specify a point in 3D space. Then we, so to say, define a cube with a certain extent, which is centered at that point. And now what we do is we render 6 images, and these images are rendered by just taking the cube center point as a center of projection, or as a camera position, and rendering the scenes as seen when looking through the 6 cube faces. So the 6 cube faces are then becoming our virtual view windows, and we are now simulating what we see when looking through these windows by just rendering the surrounding with the cube center being the camera position and the viewing parameters defined properly. So the cube map then in fact captures the incoming light through the 6 faces of that cube, which is centered at the environment center, which we have defined. And as I said, we generate this by rendering the scene 6 times from the cube center with the respective cube face being the viewport. That is the way how we create these cube maps. So we see an example here from Wikipedia. So we have a scene like the one here. So we define the cube map center point, the point here, and so we have these 4 objects, and then you define that cube with a certain extent into all the 3 spatial directions, the X, Y, and Z direction. And then what we see here is now the 6 images which are rendered when looking from the cube map center through the 6 cube faces into the surrounding. So you see here, that is what we see when looking through that face. And then if we look through that face here, then we see what we have here. And if we look through the top face, then we see the gray sky here. If you look through the down face, the bottom face, then we see the checkerboard pattern, and so on. So these are the 6 images we generate here, and which are then stored in one single cube map, which, as I said, can actually be interpreted as a texture which is comprised of 6 textures. So the cube map is stored in 6 2D textures. And here what we do is we use a left-handed coordinate system, so with the thumb going up, with the pointer pointing into the screen, so to say, and with the middle finger pointing to the right, indicating the X coordinate axis, the thumb pointing upward indicating the Y coordinate axis, and the Z, the middle, the pointer pointing into the wall indicating the positive Z direction. And then we see, for instance, if you look at this, if we look now along the positive X, then and we render an image, then Y is pointing upward, X is pointing to the right according to our left-handed coordinate system. And if you now look at the local texture coordinates, the texture coordinates, we say that U is pointing, so to say, up, V is pointing to the right, and they start here at 0, 0, and then go here to 1, 1. So now if we, for instance, render along the positive X axis, no? Then we just have to again keep in mind the left-handed coordinate system, and now it's clear what we have. No? If we now position ourselves at the coordinate center, no? We now look at along the positive x coordinate axis, no? And then again y is going upward. And now the pointer, no, is going to the left. The pointer indicates the positive z, meaning that into the opposite direction, then here we have the negative z. Yeah, and so you can just go through all the 6 cube map faces here, and determine, depending on the assumption of a left-handed coordinate system, you can determine to which of the x, y, and z, the positive x, y, and z, and the negative x, y, and z directions, the local UV coordinates of the texture that is generated correspond. So now, what do we do with the cube maps? So now, first of all, how do we access? Now, let's say how do we actually make use of these cube maps? So now that is, for instance, what we see here. Now, so let us assume that now here that the bold lines here, they indicate the surrounding scene, which is saved in a cube map. Yeah, so we are here in 2D, meaning the cube map would just be comprised of 4 one-dimensional textures, which have been generated in that pre-parse, where we have placed the center of the cube map here, and then have, let me indicate that, have rendered out of the 4 sides of that 2-dimensional cube map, to see what is seen from the surrounding scene when looking through these sides. Okay, let me just remove that here again. Okay. So now let us look at a certain point here. That is now here a point on a surface, and we are looking from here. And now let us first of all forget completely about the cube map. Let us just ask, okay, we want to determine the point of the environment which reflects in that point here towards the viewer. How would we do this? For instance, if you would have rays at hand, if you could use rays, you would just say, okay, so we are looking from here along that direction onto that point. Let us assume we have the normal vector here, so we can compute the reflection vector, which is this one. And now let us assume that this is here the surrounding. We would simply follow that reflection vector here until the first intersection with the surrounding environment. And what we see here, so the color of that point here, that will then be what is reflected towards the viewer when looking along that ray V. Okay, so and now you see immediately how we can actually obtain that point here by using a cube map. Because the cube map has been created by rendering through that virtual view window. And so we have rendered the surrounding, or projected the surrounding into that face here, into the cube map face, with the cube map center being the center of projection, meaning that this point here would have been projected onto the point here in the cube map. And now it's clear what we can do. Once we have the reflection vector, we simply can look up the environment point, which is seen along that reflection vector, by reading this value from the position which is indicated here by that red dot here in the cube map texture. So because in this pre-process where we have generated the cube maps, we have projected the environment into the cube map faces, and meaning that now the cube map textures, they essentially contain the projected environment, meaning that once I have now the reflection vector, I can just say, okay, by using that reflection vector, I can determine at which location in the cube map texture the point which is seen along that reflection vector is stored, and I can just look that point up, or the color of that point up. And the advantage I have here is, once I have created the cube map in a pre-process, no, then at runtime I don't have to do any projections anymore. No, I can just use the R vector, the reflection vector, to indicate from where in that pre-computed texture map I should look up the reflected point color. And then I just read it out from the cube map texture without that I have to do any projections of the environment at runtime. Now let me again remove that. Oops, what's going wrong here? Okay, yeah. So meaning, and keep this in mind, no, because what we need to do is, no, for every fragment that is seen, no, that was the one here, we need the we need the reflection vector, because that reflection vector essentially gives us the direction along which we find the environment point, which is reflecting over that point here toward the viewer. And because we have computed that point already and stored that point already in the cube map, now we need to use that reflection vector in order to look up the cube map. And we will see later on how that is done. So now there's a problem with this approach. Let me just again remove that all. And this is what we see here in that second example. No? But now we assume that we have an object with a certain spatial extent. Now let us assume we look at this fragment here. So we look from the viewpoint at that fragment, at that surface point here. So we have a normal vector here, and we compute the reflection vector. And again, the reflection vector, if this would be our surrounding environment, the reflection vector then indicates which point of the surrounding is seen along that direction and is then reflected over that point here towards the viewer. And now we see a problem. Now we see a problem because if we only make the location of the environment point dependent on the vector R, then we see that what is seen along that direction R is stored in this point here of the environment map, which essentially indicates the environment point which is seen here. So the reason for that mismatch is that in the cube map generation, we only consider the direction of the reflection vector R with respect to an infinitely small circle or sphere at the cube map center, but we do not consider the translation of that direction vector in 3D space. And that is exactly what we see here. Now we see here we have the point here, that fragment here, and we also have that point here, and they can both have the same reflection vector, but because they are translated about a certain distance, the environment point that is seen along these two reflection vectors will be different. And that is a problem of the cube maps, because the cube map is generated under the assumption that the object is a very, very, very small sphere centered at the cube map center. And this means if we now use the cube map in order to determine what is seen along a reflection vector, but for an object which has a spatial extent and is translated away from that cube map center, then we will obtain the wrong reflecting environment point. Keep this in mind. This is a weakness of the cube maps, and so therefore cube maps are in particular good if the environment is far away from that small cube map center sphere which has been used in order to create the cube map. If this is not the case, then you run into problems, because then you may look up the wrong environment value if you only consider the reflection vector. So now how do we actually access the cube map? So we have said we want to base the cube map access on the reflection vector R. And so what we see here is just the following. If we have now a reflection vector R, now the reflection vector R has, we know how to compute it. We will also show this on the next slide. Now the vector R is a 3-component vector with an X, a Y, and a Z component. And now I think it's clear that the largest component of that reflection vector R selects the cube map face. Just position yourself at the cube map center. Try to imagine that this cube is centered at that point, is lying around of you. And now just take an arbitrary vector, call it R, and now try to compute through which of the cube map faces this vector is going, or with which of the cube map faces this vector has an intersection. And then I think it becomes immediately clear that the largest component of that vector indicates the cube map face with which this vector has an intersection. And now once we have that intersection, then we know from which of the 6 two-dimensional cube map textures the values have to be retrieved. But then, of course, we also need to know where in the selected two-dimensional cube map texture this value has to be read from. So we need the local 2D texture coordinates. And they can be generated by dividing the other components of the reflection vector R through that selected largest component. And this then gives us the local, or the local 2D texture coordinates in the selected face. Now let me come a little more precise what we have to do if we want to implement now the cube map algorithm. So you have a fragment, we have the normal at the fragment, we have the vector from that fragment to the camera position. So this is first of all the normal here. Then E, the eye position or camera position is given. Then we can compute the reflection vector R. That is exactly the equation which we have introduced when looking at the Phong illumination model for computing the reflection vector, meaning that in a shader program for every fragment we compute that vector R. And then we select the component with the largest magnitude. So we call this component then MA, or we use a variable MA, which gets assigned that largest component. And then, depending on which of the X, Y, and Z component is the largest, and whether we, so to say, look along the positive or negative X, Y, or Z axis, we get the 6 cases which we have summarized here. So it means that, for instance, if the Rx, so the X component of the reflection vector R is largest, and then depending on whether that component is positive or negative, we are looking along the positive or negative x-axis, and then this selects the face, so the positive x face or the negative x face. And then by dividing the other components, and U is then set to Ry and V is set to minus Rz or Rz for the positive and negative case. And then what we do is we simply divide U and V through that largest component MA. And this then gives us a value between -1 and 1. And that now has to be normalized to 0 to 1, and that is just done by adding a 1 that shifts everything to 0 from 0 to 2, and now dividing through 2, that gives us finally the texture coordinates U and V in the range from 0 to 1. So you see exactly what you would have to do in a fragment shader. You have conditionals And first of all, depending on which is the largest component of the computed reflection vector, you decide whether you are selecting the positive x or the negative x, or the positive y, the negative y, or the positive z or the negative z cube map phase. And then you just assign the respective other components of the reflection vector to the variables u and v. And then, equipped with u and v and ma being the largest component, you then normalize the uv coordinates so that you are within 0 to 1. And then you can use them directly in order to access the cube map values. Yeah, some examples here. So the T-port and now the environment, which is captured here in the cube map and then mapped to the T-port. And again, let us assume, so we are looking now at that point here. We assume that we have a normal vector here, so we can compute the reflection vector R. And then with this reflection vector R, we do exactly what we have seen in the previous slide in order then to access the corresponding cube map texture, whatever texture it is. We get the relative position in that texture, and this value is then taken as the value which is seen here at as the reflection. Yeah, as we have said, physically correct reflections only at an infinitesimal point at the center of the cube. That is exactly what we just said before, that because we base the lookup from the computation of the location from where in the cube map we look up the pre-computed values, we base it solely on the R vector. And now again, if we look at this example here, we see that the very same R vector, of course, can occur at differently located fragments. And if we only base that lookup operation on that R vector, then of course we might get a wrong reflection. That is exactly what we see here on the left-hand side. How we can heal that problem? We cannot heal that problem, but at least we can make that error small, so that hopefully it is not visible again, by saying, okay, what we have to do is, if we have an object like the object here, and this object has an areal extent, and this object is not, so to say, exactly, so to say, coinciding with the center of the cube map, which is defined, then at least if the surrounding is infinitely away from that object, then that error becomes smaller and smaller. And that is what we actually see here. Now, for instance, if now we consider the cube map here, which has been selected, and now again we base the cube map lookup solely based on the reflection vectors, then we see that if we use that smaller cube map here, then we make a certain error, because we see that at this point here we would like to get the value which we see when looking through that face here of the environment. However, because we take that vector R, which is stored in the cube map here in this phase, we would essentially take this point here and assign it to that fragment as the point or the color that is reflected at that point. If we now look at the enlarged cube map here, and we do the very same, then we see that at least, if we take that R vector here, that vector R is mapped into the right cube map texture. So in order to be precise, I wanted to see the environment when looking along that R vector, which is somewhere here, because I'm using the pre-computed value with respect to that R vector as seen from the center point, I will obtain that value here. So you see the error which is now done is decreasing compared to the error which is done when I'm using the environment map here. So as we said, so at least the error can be decreased by storing the scene in a cube map that is, let's call it far away from the reflecting object. so that this error then becomes smaller and smaller. But we cannot never cure that, solve that error entirely. No? We will always have that kind of mismatch when now accessing the cube map. No, the good thing is that usually we are not so much looking at whether the reflections in an object are 100% correct, so meaning that the errors which are introduced by that cube map approach are not that important to us or are not that strongly considered when looking in particular at a dynamic scene where you focus on completely different things. Yeah, how can the cube map being constructed by using the rasterization-based rendering pipeline? So that is done in the following way, in a single pass approach, meaning that we only have to render the scene once in order to construct the cube maps. And what we do here is, first of all, we create two texture 2D render targets. And so why do we need two? Well, the first target is used to store the illuminated surrounding scene, so the cube map content. But we also need a second render target because for each of these, so to say, cube map faces, when rendering out of these cube map faces, we need a separate depth buffer, which we need in order to resolve the visibility during the cube map creation. Sometimes we call this cube map also the env map, the environment map. Yeah, and we employ here a geometry shader to raster every triangle into all 6 cube map faces in a single draw call. Now you can imagine this as follows. You submit the scene once into the pipeline, and then in a geometry shader, the geometry shader grabs every single triangle and now transforms that triangle 6 times with respect to the 6, so to say, views which we want to generate when looking out of the corresponding cube map faces. And then the geometry shader simply submits these 6 differently transformed triangles into the pipeline so that they are then rendered as if they were viewed through these cube map windows. Yeah, that's the way we can do it, just as an implementation issue here. If you want to create the cube maps as efficiently as possible, you can just employ that particular functionality here given by the geometry shader to amplify geometry in the pipeline. So,